Hello everyone. So hopefully you're here in the right place for the start to part, the design to manufacture experience. So my name is Adam Castañeda. I am an application engineer with Fisher Unitech. I'm actually based out of the Chicago office. So let's go ahead and get started. So Albert Einstein once famously pointed out, if a cluttered desk is a sign of a cluttered mind, of what then is an empty desk a sign? Well, apparently, a Minnesota study found that a disorderly environment can be inspiring. It can produce fresh insight and creative solutions. While I don't exactly disagree, you should definitely see my desk on occasion. Certain things should have a place, in particular the cell phone and maybe a headset if you have one. Typically, my cell phone ends up either buried under a heaping pile of papers or somewhere off to the side where I can't find it, and the headset can be somewhat of a hazard at times. So I'd like to open up with a nice little video kind of showing you guys what that might look like. Yes, for those of you guys who may know this face, this is actually Dave Janicki, one of our other applications engineers. He was, a part of this project as well, and was graciously able to provide us with a little, little demonstration as to why this may be applicable to, to some of you guys as well. So, I'd like to kind of come up with another quote here as well, actually one done by Plato, quite a few years prior to Einstein. Necessity is the mother of invention. So, typically, when someone wants to design something, come up with a totally new idea, this is often due to some sort of need. In this case, our need was to have a proper place to put our cell phone and our headset. And so, let's kind of take a look at our adventure through this process. The application engineers here at Fisher Unitech decided to brush off the cobwebs and put on their product developer shoes and walk the talk to solve a real world problem. We essentially used a good amount of the suite of SOLIDWORKS products. We essentially conceptualized, designed, simulated, fabricated a wireless cell phone charging stand with an integrated headset support for our desks. And so this is a complete design to manufacturing experience. Let's go ahead and take a look at an overview as to the products that we used. All right, so first and foremost, since this is a collaborative environment, SOLIDWORKS PDM managed all the design data and related documents in one secure location, tracking the design history and making sure that the entire team is working on the most current design. The electrical engineers sourced and provided the wireless charging components and LEDs, and using SOLIDWORKS PCB, we made sure it all fit. Architect 3D scanners essentially scanned a mid-range headset to be incorporated into the design concepts. Using traditional hand sketching and cutting-edge touch devices such as a Microsoft Surface tablet, we essentially our industrial designers created several design concepts, and we'll also take a look at what that looked like in a bit. All of our mechanical engineers used SOLIDWORKS 3D CAD software to actually go ahead and develop the concepts to manufacture those products. Our 3D printing application engineers used Stratasys 3D printers to generate several design iterations to evaluate their form, fit, and function. And finally, we utilized a virtual prototype and our simulation experts analyzed many aspects of each design, including stretch and strain, heat generation, plastic flow for manufacturability. All right, so let's take a look at 3D scanning. This is our hardware application engineer, Derek Ellis, using the small, lightweight, handheld Arctex Space Spider 3D scanner to capture the intricate details of this headset that we have kind of laying around in the office. And this is done, with very good accuracy and speed. You simply point the scanner at your model in various orientations to capture all that data. And then as you see here, after we load the information into the scanning software for cleanup and alignment, we can then export it out to SOLIDWORKS. Right, so our first order of business here was the selection of our electrical components. We chose a Qi-enabled device based on its favorable balance of size, power rating, efficiency, and price. It comes with a set of challenges and proximity requirements to the receiving coil, but we'll get to those challenges in a few minutes. We also selected a LED strip light based on their low profile, side emitting light, and it can be easily cut to size, so we can essentially control the length very easily. And with those components sourced, the conceptual ideation process can begin, knowing the physical sizes and constraints of the internal components. So one approach to product development is form over function. Here at Fisher Unitech, we took the exact opposite approach. So we wanted to take function into account first and then make a nice form over that. So let's take a look at that process. So our industrial designers bridged the gap between engineering and art. Todd Myers and Laura Nickerson conceptualized various stands and maximized accessibility while minimizing the footprint on your desk. So let's take a look at that process. All right, so we decided to move forward with two different concepts, the transporter and the holster. The transporter has an ultra slim profile and is focused on portability at its forefront. The back essentially has some hinged levers that become stabilizing feet and an upper hinged arm that supports the headset. And from the front, we have a nice little shelf to essentially hold your phone in place. The transporter was designed to fold back into itself and be tucked away into a computer bag or a desk drawer so you can easily store it or take it on the go. The holster mounts to the laptop monitor, essentially removing both the cell phone and headset from the surface of your workspace. There were three initial concepts, with the phone either in landscape or portrait, and either mounted to the top or to the side of the monitor. The headset is again supported off to the side of the phone, and a channel of light can emanate when the charger's on. So we'd wanted some feedback to show us that the charger was indeed on. So with our design directions chosen, we went ahead and began development. So right from the start, we recognized the need for a collaborative PDM environment. A group of application engineers working on this project have to work jointly on ideas to overcome design challenges and share, obviously, tons of files. The PDM specialists allocated some space on one of our non-production servers and created a virtual machine to start a PDM professional vault. Using the wizard with just 13 simple clicks of the mouse, we created a new PDM quick start vault. And we easily modified the workflow to establish a simple environment robust enough to support our needs and our demands. But as we began to use PDM, we came to the realization that we have many individuals working from several locations. So the introduction of a VPN was very critical, as I'm sure many of you who work either from home or work from a remote location, being able to VPN into your network and access the PDM vault is obviously critical. We're all not in one location, so we went ahead and set up a VPN using Soft Ether VPN, and that allowed us all to essentially access the vault from wherever we were. Here's a nice little picture, kind of showing our PDM vault set up with some of our files in there as well. Okay, so let's go ahead and move into the development. And so this includes mechanical engineering, electrical design, design simulation and validation, in addition to 3D printing. It's really hard to think about all these as individual tasks since they all kind of happened at the same time concurrently. And instead, let's take a look at the journey for both the transporter and the holster from essentially beginning to final prototype. Let's again start off with the electronics as it applies to both designs. Some of the design challenges here for the charging coil specifically was just the location. The charging coil, again, depending on the location, that will affect our efficiency. And then we also wanted to take into account how we would illuminate the LEDs and how we would actually power them as well. So SOLIDWORKS PCB is a standalone schematic capture and board layout tool. We can seamlessly collaborate our board designer back and forth within SOLIDWORKS. With our library of components, we complete our schematics and board layout, in our case, the wireless charger's PC board. In this case, we actually wanted to update the board design with a new reference board. So what we're able to do in SOLIDWORKS is actually import the new updated geometry and simply use it as a reference to now update our original design. So what you're seeing here is the alignment of the two boards and then the editing of essentially the original simplified board model. So we go into the sketch, simply delete the original geometry, and then update it with the new board using a convert entities task here. So what you're seeing here, simply replacing that geometry. Now with that PCB updated, we can push those changes back into SOLIDWORKS PCB. You can see here the changes being shown in PCB and able to essentially compare and contrast the original design to the now updated design. Okay, so looking again at some of those design challenges, to receive a 75% minimum power efficiency between the charger and the phone, the charger's location for the coil has to be within 0.2 inches of the receiving coil with relative concentric alignment. So again, this is affecting directly the charging rate of the actual phone charger itself. And then for the LED illumination, if we want it to come from inside of the housing, how will we power these LEDs? And again, looking back at that coil location, certain phones have it near the bottom, certain phones have it closer to the middle. So this is just a couple of things that we had to take into consideration when designing our charging stands. A couple of the solutions that we came up with for our problems. For the depth itself, the max distance between the coils having to be 0.2 inches, we simply just had to minimize the wall thickness between the charging coil and the phone itself. And the concentricity, we can assemble the coil in different locations and offer several SKUs. So what we mean by this is, let's just say most iPhones have their charging coil near the bottom, and then most Androids have it near the middle, or most Samsungs. We can essentially offer, a SKU for Apple devices, a SKU for Samsung devices, and this is something that's pretty common in the industry, since it makes more sense to offer that variation in design versus having one universal charger that can sometimes be good for one product but be bad for another. So we decided to go that route. And then the LEDs are simply powered by jumping power off of the PCB. And as for the illumination, mainly focusing on our first and third ideas, we actually went ahead and used a radiation, essentially light radiating through a plastic wall. So just having locally thinned walls we're able to radiate through, and then using transparent or translucent materials. All right, so let's go ahead and take a closer look at the journey of the transporter specifically. So the engineering challenge for the transporter initially were the hinges. So in the original design, the hinges for the stabilizing feet were located at the bottom of the housing, and when in storage, the feet hinged up. Although this is, a kind of cool design, we were initially concerned that these hinges worked against gravity and they would require very hefty detents or a spring to prevent the stand from accidentally folding. So the decision was made to modify this design so that the hinges were actually based at the top and acted like a kickstand. So this is what that updated looked like. So our mechanical engineer, Dave Janicki, made some changes to the design. It stayed the same aesthetically for the most part. Now it just works better with gravity. So we overcame the first challenge of gravity, and next the hinge design strength is what we'll focus on. So what we'll see here is essentially the steps that we went through to set up a simulation to see the strain on the hinge itself. So initially we set up some contact sets for the pins themselves, and then we moved on to apply some fixtures. So in this case, the fixtures at the bottom essentially simulate the phone stand being placed on the desk. And then some roller slider supports referencing the kickstand to the actual main body. Right, now we are seeing the external loads being applied. So in this case, we are looking at gravity first, which is of course applied to the entire assembly. And then looking at the forces, this initial force is the phone being placed on the actual stand itself. And the second force is, of course, the headset in essentially laying on that back hinge. From there, you create a mesh. And in this case, the first mesh that was created was a little bit too coarse for our likings. So we went ahead and updated that mesh. Okay, so here are the results for our stress analysis, including the displacement and the strain. And so one thing to focus on here for the stress, although it looks like a bad design, we have a lot of red here. Usually red means bad. If you really pay attention to this, the maximum stress we saw here was a mere 15 psi, where the failing tensile strength limit of ABS is closer to 6,600 psi. So we're well below that maximum stress or strain that we can reach. It's just a matter of kind of taking a look at this information and knowing what to expect. All right, so let's go ahead and take a look at our first physical prototype. So right off the bat, we encounter some issues. And in this case, it was actually an issue of communication. So when we had designed this this first prototype, this was supposed to be a print-in-place assembly, which means the two black pieces that you're seeing over on the right should have been printed in place where they belong within the main housing. However, this wasn't communicated very well to our 3D printer, 3D printing engineer, and we got a couple of separate pieces which we had to finesse into place with a chisel. So in this case, we did have to break away a bit of the body, but at the end of the day, it fit in there like we expected. However, we did run into another issue now. The fact that we actually can't take the kickstand out of the body without prying it open again with without the force of a tool. So clearly we had some issues in our design that we didn't really see until we made our 3D prototype. However, the phone did perfectly sit on the stand, so we were pretty happy with that. So for our second iteration for our prototype, we did actually get it printed in place as you see here. We didn't have to force anything in place. And then we also hollowed out a bit of that stand. So now you can use that hollowed out portion to simply pull the stand out and essentially set your phone and your headset on there. However, another big issue we ran into here was we didn't really limit to the angle very well. So what you're seeing here is I apologize, is the headset kind of, overcoming that hinge there and kind of laying on the table, which defeats the purpose. However, again, the phone stood on there relatively well. And with the aid of a couple of coasters, we can see that our kind of our initial idea isn't perfect, but we're going in the right direction. So again, round 3 of 3D printing. After doing a bit of more iterative design, we implemented a stop on the hinge now. When we place our phone on there, everything's looking great so far. We place our headset on there, again, looking good. And at the end of the day, with these couple iterations, we kind of got away with a good physical working prototype, so we were pretty happy about. However, one thing that we want to do here for both of the designs is take into account, if we were to take these to market, what do they need to do? They need to be able, to be manufacturable, to be assemblable. We don't expect these to be, 3D printed in mass. One would expect them to be maybe injection molded in different pieces. So we went ahead and made a few changes to the design with that in mind. So let's take a look at that. Okay, so what you're seeing here, again, is both of the hinges were remodeled a bit so that they are able to essentially be pinched in place and then essentially clipped into the body itself. So one critical thing that we had to take a look at, of course, is with the change in physical design, will this still, withstand the forces and the pressures that we're applying to this? So we went ahead and reran our simulation. However, since most of the design was still the same, we're able to copy over a good amount of the information that we set up initially. So you're seeing here, the contact sets are the same. Most of the forces are the same. And then the mesh itself had to be regenerated, of course, because this is a new geometry. So after we ran that second simulation, we'll see that we went up to roughly 26 psi, which is still far below the failing point of ABS. However, this is a good point to kind of stop and take a look at at the results, and taking into account our initial PSI was 15, we jumped up to 26. That's almost double, which in our case isn't a big deal. But if we were already taking a design, kind of pushing it to the edge, made a change and then doubled the internal stresses, you can see you can run into some serious issues if you're not careful. So this is just a good point to say, what, if you're going through an iterative design, it's a good idea to run some simple stress analysis just to see the magnitude of change that you're creating. All right, and this is the electronics assembly for this design specifically. So in this case, we simply place the PCB and charging coil near the center, and the LEDs on the PCB itself radiate through the housing. So you can see on the right-hand side, that green light just radiates through, and when it's in use, it actually changes to a blue LED. So you have a very clear visual indication. So here we reached our final destination for the transporter. So with SOLIDWORKS simulation, we felt confident in our design by incorporating virtual prototypes at an early stage, and we validated our findings with physical prototypes. So now that we have the transporter in a working prototype here on the, we will move on to the holster itself. All right, so let's go ahead and take a look at the holster journey. So after a bit of competitive product analysis, which essentially meant asking each other, hey, which one do you like most? We essentially decided on the vertical side holster, essentially on the side of the monitor here, as you can see in our renderings. So in this case, it shared similar design challenges that the transporter did, where we didn't really think through some of the mechanical properties. So what we did here is actually ran another analysis, in this case SOLIDWORKS Premium. We did a motion analysis to accurately simulate and analyze the effects of these motion elements, such as forces and springs. And so let's take a look at what that really brought us here. Seems a little extreme. So let's maybe take another look at that. Yeah. So clearly the forces that we didn't really anticipate for here left us with some issues here. So we needed to add a mechanism to essentially keep it attached, such as a clamp or maybe a spring clip. So our engineer James designed some spring clips to be assembled to the inside of the back wall of the monitor hook. And the spring clips essentially do two things for us. They account for different size laptop monitors, and they also apply enough pressure to essentially lock the stand in place. So we went ahead and again created some 3D printed prototypes. We have our first iteration. Looking good so far. Sec. You can see here, we actually integrated our spring clip into the design, flipped it over the monitor, and it seemed to hold just fine up until you actually apply your headset to the stand, in which case it simply slides off. So clearly, we had to go back to the drawing board and rebuild the clips and maybe rethink the assembly method as well. All right, so in round 2, James made some changes. The spring clips were shortened and moved to a more accessible location. We printed the clips in a new material and in the correct orientation. Initially, we saw much better results. However, the front of the holster was lifting away from the front of the monitor and then became unstable at with certain forces being applied to it. It would simply fall off, and you can see here the results of that. We did have a casualty in our second round of testing. However, we did want to just change the mechanism entirely. So we went more for maybe a proof of concept for a clamping mechanism. So here you see a binder clip, a Dremel, some duct tape. It's not pretty, but we went through this initial little design here to maybe have a proof of concept. So let's take a look at how this went. You see initially it holds well. We have our headset, we have our phone. It's looking great so far. 30 minutes later, we're still in business. So we can see that, although this is a very rudimentary kind of test, we kind of proved that concept that maybe a clip system would work out better for us. So here is our redesigned holster. However, one thing we wanted to find out was here. There we go. So one thing we wanted to find out was the clamping force necessary to actually keep this thing in place. So we actually went ahead and set up a new study. So again, very similar to our first one. We have our various connectors, our various fixtures. So in this case, we have a bunch of pin connectors. We fixed these two faces in particular, just to simulate the fact that we want them to essentially stay in place and not move. We applied a couple forces. So again, in this case, the force of the phone being placed on the stand, and the force of the headset also being put in its place here. Here you'll see our that we created initially. And one thing to note is that we like to keep a minimum of 3 elements along the thickness just for accurate results. So taking a look at the results, we're able to check the free body forces of a specific point. In this case, it is along that back face. And what we see here is that we require a normal force of 6.75 newtons, essentially, to keep this in place. So we went ahead and sourced some springs for that. I'm sure many of you recognize this site or this page. This is from McMaster-Carr. So looking through the available springs, we found a good choice here. 6.75 newtons is roughly 1.5 pounds. And given the geometry we have here, using a spring of 1.82 inch-pounds actually worked out pretty well. But just to be safe, implement 2 springs on there. And we went ahead and made a third round of 3D printing. You can see here various different angles of the design here. And once we put it in place, put our headset and our phone on, everything worked perfectly. And third time's a charm in this case again. So this is what the electronics assembly looks like. It's a little more involved. But again, another thing we didn't take into account here was the size of the actual charging coil. So you may see a bit of more, a little more dremeling, a little more filing away at the inside to get that coil to fit. But overall, the design itself was very sound and very stable. All right, so another thing we were looking at here, again, is the ability to maybe market this a little better. Because if you're going out and creating a product, you want to create some good renders of it. And looking at this, looking at our generic kind of SolidWorks gray, it's not very exciting. So we went ahead and made a couple visualized projects. Here you have a couple of our initial iterations, playing around with some metallic surface finishes, some soft textured surfaces like on the right. We also worked with transparencies. And then to kind of emulate that LED, we used emissive appearances. So those are available in SolidWorks Visualize Professional, but you can very clearly get some very cool designs out of this as well. Right, so the final concept of the transporter, again, uses LEDs on the PCB to emit a soft ribbon of light that is complemented by the texture of the graphite housing. And the final concept of the holster essentially molds the outer housing in a clear material. So if we were to actually manufacture this, we would have the internal black portion of it be an insert, for example, and then be overmolded with a clear material. The very cool thing about using a Stratasys PolyJet printer is you can actually 3D print clear materials. So in this case, we actually have a physical prototype in hand that obviously you guys can't see, unfortunately, but it looks just like it does in this visualized render. And we did actually incorporate the 3D texture command and patterned in a little bit of the Fisher Unitech logo into our design. No subliminal messages here. We're just kind of having fun. Okay, so let's go ahead and take a look at another simulation. In this case, we are looking at how we would go about using a injection molding machine to, again, overmold our holster part. So give me 1 second. Okay, so as I mentioned, the central piece, the green part in this case, would be an insert, and the gray portion would be overmolded. Let's take a look at what that process is. So initially, you set up your meshing parameters. In this case, you'll see setting up the meshing parameters for the exterior using a 1. Assign that. From there, our mesh summary will actually indicate that we have a couple bad elements. Here, have a couple bad elements here, 0.02%. Looking into these, we'll actually see that the mesh elements actually have a bad aspect ratio. It just means that they're essentially too long and too narrow to properly run an analysis on. The mesh advisor can actually fix those for us. So very, very helpful tool here, allowing us to move forward with our analysis. In this case, now we do have to set up an internal solid mesh as well. That's what you're seeing here. Okay, and now moving on to the materials. So in this case, we have to set up a polymer material, a mold material, and an insert material. So again, this takes into account the various physical properties of each different material and each different component that we're looking at. Now we're looking at the fill settings. So in this case, you can set things like the melt temperature, mold temperature, clamping force, all those sorts of variables. And now the boundary condition, specifically the injection location. So one cool aspect of this is you can actually add a location automatically. So it kind of analyzes your mold geometry, so it's the location. In this case, we didn't really like that location, so we just deleted it and created our own. See us actually incorporating what we think is a good location for this fill port. So from there, we went ahead and checked the nominal wall thickness. It's all one uniform color, which means it's essentially a good uniform thickness. We went ahead and ran our all right. So what we see here now is the results. So the results advisor essentially provides us with a green light, which means we had a successful with no short shots. And it also provides a pretty good kind of succinct list of essentially tips to understand what you're seeing here. So if you're not familiar with the results, it provides you with a nice guide. We can go ahead and look at several of the results. In this case, the fill time. You can also see a nice little animation showing you what that fill looks like. And there we can see the end pressure that we saw. In this case, we are looking at the cooling time. So now you can see which portions of your design will have a different cooling time. In this case, where the shelf meets the body, since we have more material there, it will cool at a slower rate. Again, where we have the back piece meeting up with body, since we have more material there, it'll actually potentially create sink marks. So that's what this analysis is showing us. Now we're looking at the ease of fill. So again, all green, very easy to fill. There's no sort of traps that injection molder can't get past. Now these are actually weld lines, and where you get weld lines essentially is where two fronts of molten polymer meet up and then start to cool. So these areas would actually be very susceptible to cracking or failure. So in this case, you'd want to make sure that these weld lines aren't in an area of high stress concentration or high forces, because again, they would be very susceptible to failure. Here, wherever those two fronts meet, that's where you get a weld line. And now we are actually looking at the air traps. So these little purple dots essentially indicate wherever you end up with air traps. So again, these molds are initially just filled with air, or not really. They don't really have any material in them. Once you force molten plastic in, all that air has to go somewhere. So it essentially gets forced into these locations shown in the dots. And again, so you're just seeing a nice little animation here with times being shown dynamically. So yet another simulation we ran here was a flow simulation. But in this case, we're actually looking at the temperature profile as we ran the LEDs and the charger stand. See what that looks like. And as you run it more and more, you'll see that the surface and the internal temperatures do rise pretty significantly. And in this case, one potential issue we saw was that the steady state temperature is reaching over 105 degrees, where the actual material itself doesn't fail till 300, so that's not a huge issue. We're not experiencing any melting. However, our LEDs may begin to fail. The LED strip is actually designed to operate up to 105 degrees. So obviously we were pretty easily reaching that in certain areas. So that kind of warranted a physical prototype. So again, we can go through the virtual prototype. We'll see some concern, but now move on to yet another physical prototype, uh, showing where these LEDs are here with these arrows. We'll kind of set up a prototype and almost a torture chamber here, for lack of a better term here. So this is a do not try this at home moment. One of our electrical engineers built again, a test to essentially charge the phone and generate as much heat as possible in a very high ambient temperature. So after running this on and off for a couple of weeks, the results were we had no noticeable effect on the performance of those LEDs due to the generated heat. So again, this was something that we verified in person. We put it through essentially the worst possible situation. We saw no issues with it. We're pretty happy with our design choices. And so we essentially have reached our final destination with the holster. During these holster and transport journey, we experience the design challenges that you face every day. Having deadlines and people leaving, not being able to access the vault, delays in shipments and personalities, we lived through pretty much all of that. Developing using the SOLIDWORKS suite of products was the easy part. 3D CAD, motion analysis, simulation, flow and plastics, all being wrapped up in PDM. We made informed, calculated, and smart design decisions, and the 3D printed models furthered our insight and validated our findings. So at the end of the journey, we produced some pretty cool manufacturable cell phone and headset stands. And the corner got him. But it was definitely a very fun experience. We hope you guys enjoyed our presentation here. If you do have any questions, I know I saw a couple kind of pop in here. Can you actually go ahead and email to me? So here's my email. It's acastaneda@fisherunitech.com. Fortunately, I'm in a little bit of a time crunch right now, so I will definitely get back to you guys. If you do have any questions or want to review anything I showed you, I'd be more than happy to give you a call or those questions. But again, thank you very much for joining us.